Hola. Hello. My internet connection is very erratic today, so hopefully this will go okay. I forged a spoon the other day. Man, this looks like crap, doesn't it? But it's a spoon. Yay. Don't you want to have your cereal from that? Mmm. Okay, I guess I'm just going to get started because I don't see the number of viewers increasing. Okay, so we're going to finish up electric fields by integration today. All right? Oh boy. Excuse me. So we have 2 more examples to do, and then we will have completed all of the examples for calculating electric field that you need to know. So today's lesson, the first example is going to be an infinite line of charge with a constant lambda. So lambda is dq dx. And of course, once we rearrange this equation, it's going to tell us that dq is lambda times dx. Okay, so we'll be using that. Let's just talk briefly about finite versus infinite. If you have a finite line of charge, so in other words, it has a beginning and an end, and you calculate the electric field at point P, it is going to, basically the electric field is going to point away from this line of charge, more or less. So the electric field is going to point in that direction. Okay? So that's going to be so it has an x component and a y component, right? It's got a horizontal part and a vertical part. But now let's imagine that we have 2 finite lines of charge that are symmetrical about this point. So this piece creates an electric field that goes that way. This piece creates an identical electric field because it's symmetrical that goes in that direction. Okay, so what's going to happen if we find the total electric field due to both of these pieces? Okay, we have to add these 2 vectors, and when we add them together, we can see that the horizontal parts cancel out, and we just get a vertical electric field. Okay. Similarly, if you have an infinite line of charge, So one that just goes on and on and on from minus infinity to plus infinity. What you're going to have is, and here's your point P, is that the right side creates an electric field that kind of goes this way, and the left side creates an electric field that goes this way, and those combine to create an electric field that goes straight up. Okay, so the key point here is that whereas a finite segment of charge is going to have both an x and a y component, if you have an infinite line of charge, then the x components cancel out and you only have a y component. Okay. How did the electric field lines point if you have an infinite line of charge? So let's say you had an infinite line of charge and you're viewing it from the side. So here is lambda. Well, if the electric field is vertical, then that means that the electric field lines have to be vertical lines. So the electric field lines look like this. This is assuming that it is a positive line of charge so that the electric field points away from it. Okay, so this is how the electric field is going to point from a side view. If you imagine that the infinite line of charge is pointed towards you, then the electric, so that that's the tip of the infinite line of charge going directly towards you, then the electric field lines just points directly away from it. So this is a front view. Like that. Okay? So we're going to calculate the size of this electric field. So let me set it up. So we have our infinite line of charge. It goes from minus infinity to plus infinity. And so basically the line of charge coincides with the x-axis. Here's the origin. And here's our point P, where we calculate the electric field. The point P is a distance y above the origin. And we want to know what is the electric field at point P. So what we want to do is we want to look at a little piece of the line of charge. So maybe this little piece. And so this is a little piece dq, and it is located at coordinates x, 0. So that means that this distance right here is x. Okay. And then this distance right here is going to be, according to the Pythagorean theorem, that distance right there is going to be square root of x squared plus y squared. All right. And so this little piece of charge is going to create a little electric field that goes that way. But here's the thing. And so part of that electric field is horizontal and part of it is vertical. So this is dE sub y. Now, all right. So now because we know, according to this symmetry argument that I just gave you guys, the electric field at point P is going to point in the J direction. Okay? So there's no point in adding up the x components because I know that the x components are all going to cancel each other out in the end. So all I'm going to do is I'm going to integrate the y component of the electric field. Okay? So how do I get the y component? Well, if this angle is theta, then the y component is going to be cosine of theta. Okay, so what I'm going to do is I'm going to integrate dE times cosine of theta. All right, and dE is, according to Coulomb's law, it is k dq over r squared. All right, so cosine of theta, because these are vertical angles, cosine of theta is going to be adjacent over hypotenuse. So this cosine of theta term is y over square root of x squared plus y squared. Okay. And furthermore, I know that r, which is the distance from dq to the point P, is square root of x squared plus y squared. So that means that r squared is going to get rid of that square root. All right. And then I know that dq is going to be lambda, which is a constant, times dx. So now I plug all that stuff in. So I get j times the integral of k times lambda dx over x squared plus y squared times y over square root of x squared plus y squared. All right. Now our integration variable is x because it says dx there. And so remember, x is denoting position along this infinite line. So where does the infinite line begin and where does it end? Well, it begins at minus infinity and it ends at plus infinity. So this is another example of what's called an improper integral. So now what we want to do is we want to simplify this as much as possible. So if I notice that x is my variable, anything that doesn't have x in it can be factored out. So that's going to be y, lambda, and k. So I have k lambda y times j hat times the integral from minus infinity to infinity of dx over, and multiplying these two together, we have the first power and then the 1/2 power, so I get the 3/2 power of x squared plus y squared. So this is the point at which we have left physics behind and we have gone into the realm of math. Okay? But in the interest of completeness, I'm going to show how to do this integral. If you don't know how to do this integral, it is completely okay, because you can always, if you can get to this stage, you can always just put this into Wolfram alpha. Okay? And it will give you an answer. Or you could put it into your calculator and it will give you an answer. So, so my main objective is for you to go from Coulomb's law to an integral. Whether you can do the integral or not is not such a huge deal, because you have support for that part. So the method that you want to use for solving this integral is something called Trig substitution. And I don't know if this is in Calc AB or Calc BC, I don't know. But basically what we're going to do is we're going to let x equal y tangent of theta. So our old variable was x, and our new variable is theta. Okay, so we're transforming the integral from an integral over x to an integral over theta. So it's like U substitution kind of, a little bit. Taking the derivative of both sides with respect to theta is going to give dx equals y times the derivative of tangent is secant squared d theta. Okay, so that tells me what dx is going to become. Dx is going to become, dx, I will plug in y secant squared of theta d theta. All right. Then I have to simplify this part right here. So x squared plus y squared is going to become, now x is y tangent of theta. So x squared is y squared tangent squared of theta. And then I still have plus y squared. All right. And then I factor out y squared, because both of these terms have y squared, and so I get y squared tangent squared of theta plus 1. And this is just a restatement of sine squared plus cosine squared equals 1. So this is actually equal to secant squared of theta. Hopefully you've done that in your math class before. And then I raise both sides to the 3/2 power. Okay. And so the half is going to take the square root of that, which will get rid of the squares, and then the cube is just going to replace them with cubes. All right, it's like x squared to the 3/2 power is x cubed. All right, so just everything becomes cubes now. So this piece right here is going to become y cubed secant cubed of theta. All right. And then lastly, when you do a change of variables like U substitution or trig substitution, your limits of integration will change. Okay, so we know that x is in the range of -infinity to infinity. All right, so what is theta? Because our new variable is going to be theta. What is theta in the range of? Well, to understand that, we have to think about tangent. And you know that the graph of tangent has these vertical asymptotes. So I know that tangent of pi over 2, if you look at tangent of pi over 2, it has a vertical asymptote and it goes to plus infinity. Okay? And tangent of negative pi over 2 is minus infinity. So if x goes from plus infinity to minus infinity, theta is going to go from minus pi over 2 to plus pi over 2. Okay? So now I can rewrite my integral. Okay? So I have k lambda y times j. My new integral over theta is going to go from minus pi over 2 to plus pi over 2. The dx became replaced with y secant squared of theta d theta. And then this piece right here became replaced with y cubed secant cubed of theta. Okay, so if we look at this, I can see I have 2 factors of y on the numerator and 3 on the denominator. So once all those are canceled out, I just get y on the denominator, like that. So I'm going to have k lambda over y times j hat. And then you have secant squared divided by secant cubed. So that's going to be 1 over secant. But 1 over secant is just cosine. So this is really the integral of cosine of theta d theta from negative pi over 2 to plus pi over 2. All right? And so the integral of cosine is sine. And when you evaluate the limits, you get that the value of this integral is 2. All right? Simply 2. So we get, so bringing that factor of 2 all the way to the front, we get 2k lambda over y times j hat. That is the electric field at point P. Boom! So that's kind of a nasty little integral, but it's not that nasty, but it's one that uses a technique that you might not know about, which is trig substitution. So that is our first example. So we're halfway done. Actually, I would say we're more than halfway done because the next example is easier. So for the second example, we have a ring of charge. Yes, all that for a factor of 2. Once we get to the end of the school year, this is an interesting point. A lot of times what happens in physics is you can actually guess the final form of the answer with the exception of that factor. So, for example, I will teach you at the end of the school year how to guess almost any physics formula up to a constant numerical factor. And that constant numerical factor is whatever integral you get. Okay, whatever the value of that integral is. But notice how really the physics, what the physics says is, how does it depend on y? How does the electric field depend on how far away you are from that infinite line? That's really what's most important. The factor of 2 gives you the exact number, but if you want to just, but basically I could teach you, and I will teach you, how to guess that the final answer is going to have this form. I won't be able to tell you how to guess that there's a factor of 2 there, because that's the part that comes from the calculating the integral. But we could actually have guessed that it's going to be something times k lambda over y. All right? So I'll show you how to do that towards the end of the year. Okay. So if you have a ring of charge, let's suppose you have by the way, it's a uniform ring of charge. So all parts of the ring have the same charge density. Of total charge Q and radius A. So I'm going to draw this, and we want to know, we're going to calculate the electric field at point P. I'm going to define where point P is in just a second. So first of all, let's imagine looking at this from a 3D perspective. So if you have a ring of charge, and you're looking at it from a 3D perspective, it's going to kind of look like an oval. Okay? Here's the center of the ring, and the ring has a radius A. Okay, so that length is A. Now let me tell you where the point P is. You take the center of the ring and you go up a distance y. So, and this is a right angle here, so this is perpendicular. So it's kind of like if you think about this ring as a plate, you're taking the center of the plate and you're going directly above that a distance y. And there's your point P. Okay. Now let's think about this from a side view. Oh my gosh. And so from the side view, the ring just looks flat, right? If you look at a plate from the side, it looks just flat. Here's the center. This distance right here would be A, and then we're going perpendicular to the center, and there's the point P. All right. And if you wanted to think about this from the top view, the point P is kind of like out of the page above the center, like right here. Okay? And so I think it's fairly obvious because of the symmetry, the electric field has to point in the J direction. Okay? Because, and it's for the same reason as last time. If we look at a little piece of charge here, this little piece of charge here is going to create an electric field that points in that direction. Okay? But if we look at the opposite side of the circle, there's another piece of charge right here that creates another electric field that goes in that direction. And those two would combine to create a vertical electric field. Okay? So just like before, when we calculate the electric field at the point P, we know from symmetry that it's going to point in the J direction. So there's no point in adding up the X components of the electric field. All we're going to do is add up the Y components of the electric fields. Okay? So this right here is dE, and this is the Y component of dE. If we call that angle theta, this right here is going to be theta. So we can see that the Y component is going to be times cosine of theta. So this is going to be J times the integral of K dQ over R squared times cosine of theta. All right. So I hope that makes sense. There's an interesting point. So the ring makes a cone of charge. I mean, it doesn't, it's a ring of charge, but the electric fields that the different parts of the ring make form a cone. Okay? And when you add up a bunch of vectors along a cone, it just points along the axis of the cone. All right. So this distance right here would be R. All right. And from the Pythagorean theorem, this is A. So you would have this distance right here is square root of A squared plus Y squared. So that means that R squared is just going to be simply A squared plus Y squared. These are vertical angles. Okay. And so I could calculate cosine of theta with this, or I could calculate it with this lower triangle. And it's going to be adjacent, which is y, over hypotenuse, which is square root of a squared plus y squared. And then a little bit trickier. So the trickiest part of this one is probably figuring out what is dq. So the reason that it's a little bit tricky is we basically have two angles, okay? We have this angle theta, and we have another angle which I'm going to call alpha. And alpha is denoting the location along the ring of charge. So remember what I said is if you have any circles involved, okay, if you have any circles involved, then your integration variable will no longer be x. It will be some kind of an angle. But we have to be careful here because we have two angles. We have this angle that we need the cosine of, which is defined up here, okay? But then we also have the angle for position on this circle. So we need two different angle variables. So that's why I'm calling that alpha. So in other words, here is alpha equals 0, and then we have our little bit of charge here, dq, and it makes some angle alpha like that. So dq d alpha, charge per alpha, is going to be total amount of charge, which is q, divided by total amount of angle around this ring. Because it's a complete ring, you're going to have 2 pi radians. So that means that dq is q over 2 pi times d alpha. All right? So now we're ready to plug in here. So we have the electric field at point P is J times the integral of K times Q over 2 pi times d alpha over a squared plus y squared times y over square root of a squared plus y squared. Okay, now here's the interesting point about this ring of charge. Every single point, every single bit of charge in this ring is the same distance from point P. It's kind of like if you have a cone, think about the base of the cone as the ring of charge, and then the tip of the cone as the point P. All of the points along the base of the cone are the same distance from the tip of the cone. Okay, so they all have the same R value. And similarly, this angle is, the angle theta is going to be the same for all of the pieces of charge too. If we look at this piece of charge, it creates an electric field that goes this way. This angle would still be theta. All right? So that as you integrate around the ring, this triangle is being rotated, but it's a similar triangle the entire time. So basically what I'm trying to say is alpha is our integration variable, but nothing else in here depends on alpha. So therefore we can factor it all out. So we have K, Q, Y. So K, do you ever do this? Do you ever, like, when you're rewriting an expression, I always make check marks next to each thing that I included so I know I don't forget everything. Times J hat over 2 pi. And then these are going to combine to make a squared plus y squared to the 3/2. All right. And then I have my integral and my dA. So I think everything has a check next to it, so I did it. Now, what is our limit of integration? Our limits of integration. We are integrating all the way around this circle. So our integral is going to go from 0 to 2 pi. Okay? Because that would be all the way around the circle. This is an extremely simple integral, okay, because it's just like integrating the function 1. So the value of this integral is 2 pi. All right? And notice how that 2 pi cancels out this 2 pi right here. So this cancels out with this, and we get our final answer for the electric field at point P is KQY over A squared plus Y squared to the 3/2 times J. Boom. All right. So, what did I want to say here? So that concludes all of the examples that we can do with the level of math knowledge that we have. So let me just summarize what we've done for the last few lessons. So you should try to master the following, because these are the examples that you can actually do the integral, okay? You have your line of charge. Line of charge. And the line of charge could be finite or it could be infinite. Okay? And your point P, it could be above the line of charge like this, or it could be in front of the line of charge like that. We've done examples for both, okay? So that's one that you could do, all right? You should be able to do a circular arc of charge. And in this case, your point P is at the center of that circular arc. So if you were to complete the circle, it would be at the center of the arc. Okay? And then the last example would be a ring of charge. And the only place that you would need to calculate the electric field is a point that is on the axis of symmetry of the ring. Okay? So if you have mastered these 3 examples, you can basically do all of the ones that you can do. Now there are a couple more that it is possible to solve and calculate the electric field by integration, but it gets just way more complicated. Like the level of math goes up rapidly, and you have to know about things called special functions, and it's just basically you start to get into the realm of just looking up the answer. You set it up, and then you look up the value of the integral. Okay? Which maybe I'll show you in the Zoom room. I have a textbook that really goes into depth on some of the additional ones that you can solve, and it's just like, it's just not very fun. Okay, so that's my lesson, and